All right. All right. Hi, everybody. We're now recording work 3. This is going to be going over electric current and capacitors. I just briefly wanted to just kind of make sure we're all clear with series versus parallel. And then we're going to even look at this as it applies to resistors. But just for now, we're working with capacitors. And we know that these junctions denote the fact that these guys are in parallel, and in series, it's just continuous and go all the way through. Other than that, please sign in. I always forget to put the QR code on the, I always forget to tell everybody to do that, but please do it. It's actually very important for SI. Other than going over the worksheet, at the end, I'm going to go over, I think it's homework number 2, question 4, because I got so many emails about that. So I'm just going to go step by step through each of those. So if you're just here to watch that, just skip to the end and I'll be doing that on the board behind me. So first, let's just go over some of these equations. I'll give everybody a second to write this down. I'll pause the recording for while we copy. All right, and we're back recording and everything. So let's hit this first question. This one's pretty easy. We're just going to be working with these equations where it's resistance of a wire with a cross-sectional area. So let me just first talk about the question. So here we're calculating a ratio of resistance of a 10 meters of aluminum wire that has 2.2 millimeter diameter to a 24 meter copper wire that has 1.8 millimeter diameter, and they gave us resistivity values. I always mess up on that word. I'm going to do it every single time, so stay tuned. And they gave us that for aluminum and copper. So we know we can just break these apart. We're going to be working with a ratio, so we're going to know to combine them at the end. So just bear with me and ignore everything except for this equation right here. So we know we're going to be using these equations, right? Like we know we're looking for this resistance ratio, but how do we know to choose the scenario, this scenario over here that includes area versus this one? And that's actually because they gave us elements of a circle's area, they gave us a diameter. So what we can do is set everything up, we have this constant resistivity value, we have a length, and then we know the area, which is just this diameter divided by 2 squared times pi. And we know to treat it as a circle because they gave us diameter. And this is what pops out as our value for that. And same thing over here, we're just going to use that resistivity value that they gave us. We have a length, and again, they gave us a diameter. So we know to divide by 2, square that, and then multiply by pi. And then we get 0.158 ohms. At this point, we're looking for a ratio of aluminum to copper. So aluminum over copper, plug in our values, and we get a value with no units because ratios don't have units. So that one should be pretty clear, and it's just to kind of introduce this equation, that being the resistance of a wire with an area. Okay, so that one's pretty easy, so we can just keep going. Next, we have some unit length, that's 4.8 meters, of a 2 millimeter diameter wire, and it carries a 750 milliamp DC current when 22 millivolts is applied to its ends. So we're going to first find the resistance R and then the resistivity, that rho value. So first we're going to use our equation. This one right here, we're going to rearrange it. And because we're solving for that R, they gave us that voltage and, they gave us the current and they gave us the voltage. So we can just solve for resistance. Next, we're going to be solving for this value. Again, we're going to choose the version of it that includes the area. And that's because we have a diameter. And we just kind of solve in the same way, except here, diameter divided by 2 squared times pi. We have that resistance we solve for in part A, and we divide it by that length, which they gave us right here. Okay. And these are meant to demonstrate the interconnectedness of these equations and when you got to be paying close attention to them. Any questions on this? Okay, let's move it on. So here we have a student hanging on to a DC electric transmission line with a current of 4,100 amps with both hands. The line has a resistance of 2.5 times 10 to the minus 5 ohms per meter. Here, this is something per unit length, so let's keep that in mind. And the student's hands are 1.5 meters apart. What is the potential difference between our hands? So here we have a current, we have a resistance, and we have some length. Important to note here is they didn't just give us the resistance, they gave us the resistance per unit length, that being meters. So when we solve, we're going to need to cancel out those meters. And you can just see how, like, mathematically, we just plug in that distance right here and end up canceling out the meters. But that actually lets us treat this as that value, but in ohms, not as ohms over meters. So again, we're going to use that. We're going to use Ohm's law, and we're just going to solve it out for V. All right, real comfortable with that? This is going a lot faster than the in-person one. I almost forget that these ones go way faster. So if there's any questions, please stop me. I'm happy to slow it down. All right, let's move on to number 4. So here's one of these scenarios where we have a circuit and then they gave us a capacitance for each capacitor and we're looking for ratio Q3 over Q2. So this one has less to do with finding that equivalent capacitance and, equivalent capacitance and then solving backwards for some charge across the whole thing. It's more to do with what these definitions are right here. So that's kind of the takeaway here. Q is constant, so charge is constant when capacitors are in series. Sorry, right here. And then V is constant when capacitors are in parallel, and that's right here. And the point I wanted to make here is just watch out for these junctions. It tells you where to think parallel and then where to think series. So between like each one of these ones, you can see there's a junction here and a junction here that tells us these guys are parallel. And then here it's kind of a straight shot all the way through that tells us they're in series. So we know some way or another we're going to be wanting to pull out a ratio of Q3 over Q2. So that's what we're dealing with. So first we need to find what Q3 and Q2 are. So to do that, I mean, you can do this in either direction, but I just wanted to start with finding the charge on Q2. And remember, Q is constant when they're in series. So you first need to find the capacitance they both share. So, we do that with that inverse addition right here. We work that out, get down here. And we know that C1 and C2 are equal because they all have this capacitance of just C. No number question, right? Next, we're looking for this Q value, again, constant. So we just need to solve. And we have an expression for what Q2 equals. And 3, this is kind of where it's a little bit more tricky, but all you need to do is solve for Q3 independently because V is constant when they're in parallel. So all we need to do is just identify that one little guy. So V3 equals V, we know that. Q3 equals C times V. So now we have a value for Q2, we have one for Q3. So we're just doing Q3 over Q2, we plug in Q3 over Q2, and we have some nice cancellation that comes out, and we end up with like 1/2 in the denominator, so we know to flip that, and it ends up just to come out as the integer 2. Okay, so the main point of this one, again, is just remembering that the charge is constant, capacitors are in series, and then the voltage is constant when they're in parallel. All right. Next. So here we have
I have a question.
Yeah, go for it.
For the last one, why didn't you calculate like the parallel like atom like C, like all the C's together?
That's because we already know the voltage is constant and all we actually needed was Q3. So as long as we already know what C is and we know V is constant between all of them. So it's just going to be that Q3, right? Like these guys are both constant throughout all of them.
Okay, thank you.
Mm-hmm. So here we have another question where it's more about this takeaway right here, but let me first explain. So it takes 18 joules of energy, that's potential, to move a 0.3 microcoulomb charge, that's little q, from one plate of a 15 microfarad capacitor to the other. How much charge is on each plate? So first we're going to draw out, a parallel plates, minuses and pluses. We use a test charge, which is plus. And we need to know which way this arrow is pointing. We know that it points towards the plus because potential energy is given as a positive. And therefore, it's going to be going from minus to plus. Okay. So here we know what the delta PE equals. We can express it as this equation. And we know we're looking for this delta V so we can find the charge. So next we just have to plug in our 18 right here. And then our charge of that test thing. And we get our delta V. At this point, what we need to do is plug it into Q equals CB, and we're going to be able to pull out the charge right there. That's 0.9 coulombs. So that's kind of the important point right here. All right. Next. So here we have kind of a longer one. So I'm going to just go pretty step by step. We'll just zoom in though. So we have a power station that's delivering 750 kilowatts of power to a at 12,000 volts to a city that's 5 kilometers away through 2 copper wires. They gave us that resistivity value. The wires have this radius, 5 millimeters. What percent power can be saved if the electricity were delivered at 50,000 volts instead of 12,000 volts? So this is a kind of common test question. And then just like the way to think about it is like we have these high voltage lines to transfer electricity from power plant to our house, right? And the reason why they have these super high voltages is that the power lost in that scenario is much less, as we're going to see. So that's something to keep in mind when you solve these. When we know we're going, like we're doing a scenario with 50,000 versus 12,000, you would accept that, expect that power loss value to be much less in this scenario than this scenario. All right. So every wire has some bit of resistance, not everything's perfect. The exception is when we're drawing these, circuit diagrams, we assume that the straight line wire has no resistance, but that's just kind of, us giving some artistic freedom to the physics questions. So what we have to do is answer 2 questions, that being how much power is delivered through the wires, and then how much power is lost through the wires. And we need to do this for both scenarios, that being the scenario in which it's 12,000 volts and 50,000 volts. So first, I'm going to call it P delivered. Here we have a current one and a V one. Let's first find this current. So to find that current, we're going to have power over the voltage, and then we have 62.5 amps pop out. So now we know what's delivered. We need to find what's lost. So this is how we're going to do that. However, we don't know what the resistance is, but we do have that resistivity value. We know the length of it, that's given right here. And we have the area because they gave us some radius value. So here, resistivity times that length, convert to meters. We have a radius and squared times pi. We now have the resistance value. At this point, we can plug in to find P lost. Here we have our current squared times resistance. We have our P lost. So this represents the power lost in the 12,000 volt scenario. That's significant right there. Next, let's look at P delivered. I'm going to call it P delivered prime so we don't get it mixed up here. Same setup. We're going to find that current that it has using the same equation. At this point, we're looking for P lost. Okay. And then, I'm telling you right here, but the resistance is the same. Don't get confused when you're working on this thinking it's something else because it's a different scenario. No, it's the same wires. So we're actually going to use the same resistance from up here. So keep that in mind. The only difference now, of course, is we're going to be using this current, 15 squared times 2.14, and we have this percent lost. Here, we know that we save power in scenario 2. I told you to expect that when the voltage goes up. And then, using our Gen Chem equations, we're going to do that percentage difference where it's, this P lost minus P lost prime divided by P lost as here times 100. And that's how much power we're going to save in scenario 2 in the case we're using the 50,000 volt wire. All right, so that's kind of the big one here. I apologize that this goes so quickly. I need to find a better way to do these online ones without the iPad, but for the time being, this is all I can think of. But if you guys have any other suggestions, please let me know. Other than that, I was going to talk about that question number 4, but how about I pause the recording and let people in Zoom ask questions, and then we'll resume. All right, so right now we're going to be doing that question number 4 with the whole switch situation. I already wrote down what they gave us, C1, C2, and then that 240 volts. We're given this as C2, C1, and down here we have C2 and C1, okay? And this is point C, and this is point D. Also, people in the Zoom, if I start to like write off or you guys can't see, just speak up because I don't know, I'm not gonna be paying attention. So the first thing we're gonna do is find that that voltage between that difference of voltage between VC and VD. Actually, let me pull up the question real quick. Let me pause this. I didn't even pull it up. All right, sorry about that. We're back. So we have the 4 capacitors shown initially uncharged when the switch S is open. Like I said, we have those 2 capacitor values. We have a potential difference of 240 volts, and it's applied between points A and B. So we're going to first determine the potential difference between points C and D. So how do we do that? Let's first start by, finding that equivalent capacitance. So let's circle this guy up. So right off the bat, we know that this is all in series. Right, so series, I'm just going to write S. And to do that, we know the inverse addition equals 1 over C2 plus 1 over C1 plus 1 over. Sorry. Okay. At this point, we can just clean this up. So 1 over C1 plus 1 over C2. We just got to plug in everything, and then I'm just going to be skipping like those easy steps. And C equivalence comes out to be 0.1. That's 6 zeros, and then 6 7. Okay. Afterwards, we can now find that that charge. So that's Q EQ equals CEQV. All right. Plug in that value we just got. That's 6 zeros. 6 7 times 240. That comes out to be 0.12316 coulombs. Okay. So this part right here should be pretty. We should be pretty comfortable with. I'm going to erase this part. And for this next part, we're going to discuss like how to get that potential difference. So the first one we already know. We know that the potential difference between points B and A is that 240. And the subtraction is final minus initial. So I'm going to draw this dotted line to represent that voltage drop right there. So that being VA final minus VB, which is initial, and that equals 240. That's given. So the next thing we're going to be looking for is that VC minus D. So that means we're going to be ending at C and starting at D. That's going to be a solid line. I'm going to draw that from D, wrap it around to C. So, final minus initial, VC minus VD. And what does that equal? QEQ over, remember capacitors in series have the same charge. Yeah, so capacitors in series have the same charge, so that's why they're both going to be that QEQ, and it's going to be over C2, and plus, same guy right here, QEQ over C1. All right. At this point, we have everything we can plug in. We just solve for this over here, and then C2 and C1 are given. This guy comes out to be 120 volts. All right. So that's part A. That's pretty easy. I think that we're all agreement on how to solve this one. So let's move on to part B. Also, people in the Zoom ask questions when ready or when need be. All right. Part B. We're looking for that charge after it's closed. So let's draw our diagram again. Point A, point B, switch is closed, point C, point D. Okay. So here, we know that the current's never going to reach this side. It's going to go through this path of least resistance down that way. So what's acting right now are these guys in series. Oh, again, and this is C2, C1, and it's C2, C1. All right. So we're going to find this new equivalent capacitance. Again, in series, we're going to do that inverse addition. So let's do 1 over CEQ equals 1 over C1 plus 1 over C2. You're going to work all this out, and it's going to come out as 4 over 3 microfarads, right? So that part makes sense. We should be comfortable with that. We're not going to be looking for that charge to the left of the switch. So how do we do that? We're going to plug in everything into this equation. I'm just going to erase this number of equivalent capacitance 4 over 3. All right. So that's that QEQ prime equals CEQ prime times V. These stay the same. We just solved this as 4 over 3 times 240, and that should come out as 320 microcoulombs. All right. So that's for these guys. It's for these two right here. So what about to the right of the switch? Well, to the right of the switch, we just got to think about it. By definition, we know that like to measure a current, it's going to be some charge over some amount of time. So in the case that the current, and we can rearrange that equation, right? So we have like I equals Q over T. So IT equals Q. So that's a current over time equals what the charge will be. We know that no current is acting over here. So this equals 0. So this equals 0. And that's just by simple math. And you know, like nothing's happening on this side. That's why it equals 0. All right. Again, this part B is not why we're here. This is part 3. So let's discuss. The actual math is easy, but the explanation is lengthy. So stay with me when I do that. I'm going to do the math first, so we have something to reference, and then I'm going to do my explanation afterwards. So in part 3, we're asked, I'm going to read verbatim. We're asked, determine how much charge flows through the switch after it is closed. So the key words here is very specific. It flows through the switch. We know we're looking for some change in Q. I'm going to call it Q double prime. We know that there's like a situation where it's before and after. So final, let's call it Q final, Q fin, minus Q initial. Initial, we already discussed. Like when that switch is open, there's no current going to be there. That guy's going to equal 0. Next, we're going to plug in right here. Again, if you kind of intuitively think, it's going to be negative 320 microcoulombs. So this was something that I was having a hard time with. Even myself, I thought it would be positive, but I talked to Dr. Nemichansky, and he told me to think about it in the direction in which the charge is going. So let's think about it. Okay, so let's just write the answer. Minus 320 microcoulombs. Okay, you know, that was given. That's easy math, but let's discuss why. So by definition, a charge minus Q flows onto the plate connected to the negative terminal of the supply. So what am I saying? I'm going to erase this. We are agreeing here that it's negative according to the answers. So what am I saying with that statement? Let me show you. We have a simple circuit. Let's do like this. Right here. And this. You know, it's the plus side, it's the minus side. We're going to have negative charge flow onto the plate connected to the negative terminal. So that means we have a minus Q flowing this way. And that means minus Q is going to be building up right here. As that minus Q builds up, the charges minus Q need to flow off the plate connected to the plus terminal to kind of equalize that charge. So another way to think about that is, with the switch open, the circuit is broken. The plates are neutral. There's nothing going on between the plates. However, once that switch closes, there's a current flow happening. negative charge flows towards the nearest capacitor plate. So in this case, negative charge is flowing towards that nearest capacitor plate. That's right here. Yikes. That's right here. This guy. And to counteract that, and to equalize, the minus charge leaves this plate. Leaving a plus charge behind. So I'm going to say it again. When it's closed, that negative charge is going to flow towards the nearest plate. And to counteract that, to keep this plus, the minus charge is going to flow away from this one. So if you're to finish this diagram, it would look something like this. Flows towards the nearest plate. It's minus plus, we know that. So the minus builds up here. To counteract that, the minus flows away from the plus plate, like this. And this side stays plus. So how does that apply to our example? You got to think about it. We had this point A right here. I'll let A. This is our capacitor. Continues. Switch closed. Capacitor. Point B. And here you can imagine like there's a ghost battery. Ghost battery right here. That's basically how you can interpret that. Ghost battery. We have that, that switch closed current flow towards the nearest capacitor plate. So that means minus Q is flowing towards the nearest capacitor plate. That minus charge builds up on this plate. And to counteract that minus right here, and to keep this plus, we want this to be plus Q, the minus needs to flow this way. So that's why at this point, there's minus Q within that wire. I'm going to say it one more time. I'm going to look at my notes so I say it correctly. With the switch closed, the current flow, like i.e. the current flow, is negative charge flows towards the nearest capacitor plate, creating a negative charge on that plate. To balance that, the negative here will flow away to keep that positive. So that means when that wire is closed, there is a negative charge going through it to head back the other way. And then kind of that same thing will happen here. That minus Q will build up. To counteract that, to keep this plus Q, the minus Q will go this way. So I know that's a lot. I'd say like if you want to jot it down, when the switch is open, the circuit is broken, the plates are neutral, no charge going through. That's why we set it to 0 in the initial scenario. However, with the switch closed, negative charge will flow towards the nearest plate. And to counteract that, the minus charge will flow off this positive. To keep this positive, the minus charge will flow off. And that means through the wire, there's a negative charge acting. That's why we plug in the negative 320 microcoulombs. Period. That's that. And also you'll see like I didn't draw the capacitor that's on this side and whatever. And that's because there's nothing acting there. So I just didn't even include it to make it not complicated. But that's besides the point. The point is what I said about how the charge flows towards the nearest capacitor plate. And then to equalize, minus charge leaves this plate and it leaves that plus charge behind. All right, that's for homework 2, for part 3. Everyone's asking questions about it. I think that should clear that up. I'm going to end the recording now. If any people are in the Zoom still, ask your questions. Thanks for watching, guys. Do the QR sign in.